So again, I'm recording this right now like I would for, almost all of our lessons, barring some technological catastrophe or, where I just forget to do something. And I'm doing this inside of OneNote, so this is going to be in the content library. So this isn't like content that you'd be responsible for on a test or a quiz. It's just kind of me talking about what we're going to be kind of working towards here in the course, specifically this first semester. So the focus in first semester is trigonometry. When you look at this word trigonometry, the prefix or root word is referencing what? 3, and specifically 3 in regard to, so if we go tri is 3, right? Put an extra G in there, you start thinking maybe triangle, yeah. And these triangles are kind of the fundamental starting block for this area of trigonometry. So if you guys think back to your geometry class, what are some things that you remember about triangles? So there's no wrong answers here. Yes. 3 sides. Great. Okay. What else? Okay. What were some of the different types of triangles? Right would be the based on angle measure. And then you had scalene, isosceles, and equilateral were based on side length. Mackenzie? Okay, so you'd say like the sum of the angles is, or interior angles, I probably should specify, is 180 degrees. Good. What else? Is there an acronym you remember about when we talk about triangles? Okay, so yeah, so that's referencing either like similar or congruent figures. There's a side angle side for both similarity and for congruence. Oh, did OneNote just freeze on me? Okay. Okay, very good. And one other acronym that wasn't exactly the one that I thought you would say, but it's a good one nonetheless. Yes. Yeah. And SOHCAHTOA is an acronym to help us remember the definitions for sine, cosine, and tangent. So what sine, cosine, and tangent are doing, or how we define them in our geometry class, was we said, okay, we have a right angle, or right triangle, and we specify one of the acute interior angles of that triangle, then we know that any other right triangle that has that same acute interior angle, those have to be similar, right? Because they have the same angle measures. So if this triangle, say, has side lengths A and B, and this triangle has side lengths C and D, that the ratio of those side lengths has to be equal all the time, right? So we create a function then that ties that angle measure, in this case tangent, to that ratio of side lengths that is constant all the time. Does that sound familiar-ish? So this was our basic geometric definition of sine, cosine, and tangent, where it was tied to right triangles. Now, if you're in the honors geometry class, we extended that definition to include sine and cosine on angles between 0 and 180. Do you remember how we did that? There was two things we had. We had the law of sines and law of cosines that allowed us to do sine and cosine inside of non-right triangles, but it was still tied to a triangle, right? So the first thing that we're going to do in this, well, not the first thing, but the first thing we want to do for trigonometry is we want to start building out this definition to extend beyond triangles. So in your geometry class, when you talked about an angle or an angle measure, you're always talking about this distance here, right? Or this measurement. You would never talk about that measurement, right? Everybody's good with that? Now, there's a number of real-world situations where that green measurement may be of value, where maybe we would want to talk about that thing as a reasonable angle. So imagine that you're doing some kind of navigation. You're flying a plane or piloting a ship or just like walking through a field. If you're not on a grid, left and right don't really have any meaning to you, right? Like, how far are you turning left or right? So imagine you are here and you want to get here. So one way you might do that is to turn that many degrees to the left. Now, if you're going back, you can either change the orientation or you can continue turning in the same direction you were turning before, right? Does that make sense? Now, in terms of communicating directions to somebody, it's going to be massively easier if everybody is always turning the same direction, right? We'll just turn a bigger angle everybody's turning the same direction. Rather than being like, oh, okay, so you do this much, and then you flip and you're turning, and then go back the other way, and it's like, when do you know which way we're supposed to be going? Which way would you expect to be turning? If we all decide we're just going to turn one direction, then it's very clear as to like, okay, that's what I do. So it's certainly a situation where like an angle like the thing in green there that I drew could be really something that has meaning in a real world scenario. So the next step that we'd want to do is we want to extend our definition for sine, cosine, and tangent out to include angles that are bigger than 180 degrees, that are impossible to be tied to a triangle, right? You can't have an angle bigger than 180 degrees in a triangle. Okay? So that's the first thing we'll do. After that, now imagine that this real world scenario. Let's say you have some kind of machine where you have parts that spin. Imagine like the drive shaft for a car. So the drive shaft, the engine spins the drive shaft and it goes and it transfers that to the wheels and it makes the car move forward, right? Say you want to find out how much that drive shaft spins in a second. Well, you're talking about multiple rotations, right? That's essentially an angle that's bigger than 360 degrees, right? That's something that could easily be valuable. And now, if the drive shaft spins this way and drive, what's it going to do if you put the car in reverse? spin the opposite direction, right? So if one way is a positive angle, how would we represent the opposite direction of spinning? A negative angle. So our next step is going to be, okay, can we extend this definition yet further to get any angle size, whether it's as big as you want or as small as you want, positive or negative, 0, it doesn't matter. We should be able to come up with a value for sine, cosine, and tangent for this. That's going to be really the first half of first semester is going to be dedicated to building out these definitions of sine, cosine, and tangent so that they are, instead of being very narrowly defined for like a right triangle, to being these much more robust definitions where it's not tied to a triangle at all, where you can do sine, cosine, and tangent of any number you want. So that's kind of where we're going here in the first semester for the course. In the end of the first semester and beginning of the second semester, we're going to look at other situations whose system is built almost identically to this one that we're describing. So whether we're talking about like a vector, or we're talking about, three-dimensional figures in a plane, or we're talking about parametric or polar coordinate systems, they all kind of piece together where it's essentially the same as what we're doing here in the beginning. So they all have a similar structure. So the first half of first semester is really critically important, because the structure we develop here is going to be transferred again and again and again through the course. But that's the plan. Does that feel okay to you guys? Give you an idea of kind of where we're going. I haven't talked about at all how we're going to do this, and that'll be, many days to kind of do the how and to build out a lot of the details. But I think for a course like this, it's very detail driven. Having a big picture in mind in the beginning of like what we're trying to accomplish helps, right? Gives you an idea of like, okay, so we're doing this right now, and this is really, detail driven and, but it's part of this much bigger plan, this much bigger picture. And I can see how this little detail is going to be like a step towards accomplishing this bigger goal. And in a course like this that is very detailed, I'm going to try to do that as much as possible to kind of give you the overall structure of kind of where we're going, what we're trying to accomplish as much as I can, because I think that really helps, build out your connections and see what we're doing and how it's related to what came before and what it's going to allow us to do, for the things that come after. We'll stop here.